topic today is talking about Ethereum and a little bit about blockchain in general, but everything out of the view of a developer and as a Java developer in particular. And we will also see and learn how we as Java developers can interact with this technology and what this technology actually means in practice. Yeah, a little bit about myself and why I am talking about blockchain and Ethereum here today. My name is Kevin Wittek, KeyView at Twitter, and I'm a software engineer, currently a software engineer at Atomic Jar. Atomic Jar is a test containers company, as we sometimes like to call it. But I'm at the same time also a PhD student still at the RWTH Aachen University, because the last 2 years I was the lead researcher at the blockchain research lab at the Institute for Internet Security at the Westphalian University of Applied Sciences. So I was hanging around a little bit in academia, doing academic research, also going towards my PhD, and this was all in the field of blockchain. Yes, and I landed in the blockchain area just by chance. It was not something I actively pursued, but I learned a lot about the technology, and I want to share some of the technology aspects and some of the historic context about this without all those hype around cryptocurrencies, around NFTs and so on. Yes, so that is at least is my goal, and I want you to see and understand what is actually the technology behind it, like the nuts and bolts. I'm also a consultant and a coach, freelancing stuff, but don't do this much anymore. I'm one of the test containers maintainer, and yes, in general, a big open source fan, Oracle Groundbreaker ambassador, and I'm also LinkedIn learning trainer. So there are a couple of blockchain and Ethereum LinkedIn learning workshops if you want to dive deeper into this topic in the future. Okay, so I like to give a little bit of historic context about how we came to this whole blockchain domain, blockchain hype and blockchain buzzwords and what's behind this. And what I always like to explain and the story I like to tell is that some of the concepts, some of the bits we have in this blockchain world is a logical continuation of some aspects that are really deep and far back in the computing history. So especially in the early days when we had the time sharing systems there. Because in a way, blockchain and making resources utilizable the way the blockchain does is a very is a specific form of utility computing, and it is similar to how utility computing was envisioned back in the 60s when the people were actually starting to develop those time sharing systems, multi-user systems. So the idea was always that you model computer resources after other public utilities, such as telephone network, electronic power grid, etc., so that you would have all the different computing resources by the universities. They would be connected together in a kind of a network, and then you would just in a very elastic way use the resources you use, you pay for the resources you use, and that's it. So that was the vision back then. Of course, that's not how it happened. Ultimately, the universities got their mainframes, but they were connected over the internet at one point, yeah? But not the computing resources were widely shared with each other. But still, we were moving into a direction of more interconnectivity. We had the networks, yes, and the internet. Started at the ARPANET, of course, Internet World Web, etc., etc. Then cloud computing and AWS, and of course, made the idea of computing resources as a utility even more widespread, I would say. And we think a lot, especially with things like serverless computing and so on, about utility computing. It's not called like this anymore. It's called cloud computing, but still the idea is close to utility computing. And then 2009, we got the Bitcoin network. And at its core, it's a decentralized state machine. And you pay for using this computing utility, but it is built into the system. And all you can do more or less with this is safe state in a decentralized way. But still, you can do something with it, and it has some small computing capabilities. And in 2015, the important thing happened, at least also from my opinion, is that we got Ethereum as a technology, and this is very exciting. That's where we will talk about it more. And Ethereum is basically Turing complete, but we say quasi Turing complete because it has some limitations, and it's at the same time, so it a Turing complete programmable machine, yes, that still has this decentralized state. So it's building on top of concept of Bitcoin. And now what we see currently in the blockchain domain or blockchain research world is, instead of having one big network, something like Ethereum, moving more towards concepts where we have networks of networks, and the different networks are maybe optimized for certain use cases. At least that's technically the idea of some of those things. And Andreas is asking about the slides. Yes, I will make them available afterwards. One of the core things when we talk about blockchain always has to do with trust, and that is something everyone forgets when they dive into this blockchain world. So this paper, the Bitcoin paper, which was the start of the blockchain mania, let's say it like this, from Satoshi Nakamoto, and we don't know who was Satoshi, it's a pseudonym, yes. But in this paper, he says the following: we have proposed a system for electronic transaction without relying on trust. And then people take this and always say, okay, yes, with blockchain, we solved the problem of trust. When we use blockchain, we don't have to trust anyone anymore. And this I already want to challenge a lot, because you still need a lot of trust when using Bitcoin. It's just a different form of trust. And it is, and that's generally the consensus in the academic blockchain community, it is a different trust architecture that gets established through blockchain, through something like Bitcoin, for example. So classic trust architecture is you have peer-to-peer trust when you trust someone, like another person. You're trusting another person directly, peer-to-peer trust. Then we have, so these are society trust architectures, by the way, not technical ones. Then we have something called Leviathan trust, where we trust in laws, law and order, so to say. We trust in the laws of the state, yeah, and a lot works just by the Leviathan trust. So, for example, traffic laws, yes, and they make the traffic system mostly work based on the Leviathan trust architecture. Then we have the intermediary trust, very classic example, banks. Banks are the intermediary for trustworthy transactions with other persons without doing the peer-to-peer stuff. PayPal, another example for intermediary trust architecture. And now blockchains, and for example, Bitcoin, Ethereum, other blockchains, bring us a new trust architecture, distributed trust. And now, what is the difference of distributed trust? So we are not anymore trusting the peer, or we're trusting the intermediary directly. We're trusting different properties that go together, and then by this, in general, bring us strong trust guarantees. Meaning we are trusting in the protocols and the software, and that they are implemented correctly. We have to still trust something. We have to trust that the source code and the implementation of Bitcoin is correct, and that the protocols and the people that do the proof over the protocols, that this stuff is correct. Yeah, we have to trust in this. Then Bitcoin, the security of Bitcoin and the security against double spending attacks is just a statistical property. Statistical properties are generally never 100%. At least this statistical property is not 100%. So we trust that in the long run, the statistical property will lead to a secure system, just as we trust that we will generally not have a lot of collisions of UUIDs. Yeah? It's a similar statistical property in which we trust. We trust in the cryptography of the system. In case of Bitcoin, also Ethereum, this is public key cryptography for authentication. Then we are trusting in the immutability of the state, of this distributed state, and this append-only state we have in blockchains. And we trust in the transparency that the historic state and everything is always transparently visible, and thereby we have automatic auditing built into the system. And this, in theory, allows new classes of applications and system architectures, yes, but it still doesn't free us from trust. And I like this very much, this sentence from Ken Thompson. He gave in his speech when he got the Turing Award, Reflections on Trusting Trust. You can also, if you Google this, you can find the manuscript or the how you call it, the whatever. They've written it down, what he spoke about. And he says, to what extent should one trust a statement that a program is free of Trojan horses? Perhaps it is more important to trust the people who wrote the software. And this is very true in all blockchain projects as well. The blockchain technology is often only as good as the community maintaining it. For example, an open source community maintaining it. And when it is an like unhealthy community for whatever reason, like there are not many maintainers or whatever, just a single main maintainer, it's not a very well distributed trust setup in this case already. Yeah, so this is something to keep in mind. We don't get freed from any of the trust stuff. We just move trust to a different layer, so to say. Okay, I go a little bit about the Bitcoin stuff, but not in too much detail. So yes, 2008, the paper we also see in the former slide has been published by Satoshi Nakamoto on the cryptography mailing list. So it has not been published on a peer-reviewed academic journal or anything. Yeah, it's just like a random paper, some random pseudonymous or anonymous guy or girl, yeah, we don't know, published on a on some mailing list, yes, from cryptographic from the cryptographic community. So there is not a lot of leverage behind the paper in itself. And but then 2009, based also on the concepts in this paper that were outlined, the actual Bitcoin network was launched, and then the first Genesis block was mined. So the Genesis block is the first block in the blockchain. And then we see this is here from Wikipedia. We see the number of transactions per month we have in the Bitcoin network. So it's stabilized at a certain point now. So it rises a lot and stabilized. Of course, now it's also stabilized because it just isn't able to process much faster. Yeah, but I'm not a super Bitcoin expert, so there are some ways where they try to make it faster, but ultimately the speed, transaction speed, is also kept in the network. The throughput. Yes, but what do people mostly know about Bitcoin is its use case and its usage as a cryptocurrency. That's why it became famous. It's also what a lot of the negative stuff in this whole hype is about, the cryptocurrency usage of different blockchain technologies and the tokens or coins that are involved. And yeah, we had this super big rise, but of course now it dropped down again and then stabilized again and whatever. But this is something that was never part of the concept of Bitcoin. Actually, it's not mentioned in the paper. This is a fact that happened, that Bitcoin became a speculation object, yes, a speculative asset. But this is very unrelated, in my opinion, to the actual core technology. And yeah, we have many other cryptocurrencies, and yes, they change in value and you can trade them and whatever. I'm not an expert about those things. They don't interest me a lot. And I think there is a lot of hype in this bubble, and a bubble that will burst because a lot of shady things happen in the background. And yeah, basically after today, you will also be able to launch your own coin. Maybe if you look a little bit more into the technology on Ethereum, for example, and you can do it in, I don't know, half an hour, you can launch your own coin. So most of the coins are completely useless. Okay, some more interesting technical properties of Bitcoin, and it's interesting to speak about Bitcoin because a lot of them are also implicitly or in a similar way true for Ethereum. So it is a decentralized peer-to-peer network, meaning the different Bitcoin nodes we have discover each other using a peer-to-peer protocol, same with Ethereum, yes, and then they speak with each other directly, just using peer-to-peer connections. And Bitcoin was intended for digital cash. Ethereum is intended for more. And then it is something, it's a distributed ledger. And DLT is a new abbreviation that is generally used instead of blockchain in a lot of parts in the community, because you can build distributed ledgers that are from the data structure, not a blockchain. For example, IOTA It uses something called a tangle, which is more like a different kind of tree. It's not a blockchain, but still it falls into the same class of distributed ledger technology. Then the Bitcoin uses the proof-of-work, a proof-of-work based consensus mechanism. That's also where a lot of the very bad publicity in the blockchain community comes from, that this proof-of-work consensus uses a lot of energy in a maybe wasteful way. But we will look at this proof-of-work algorithm in a bit. It's actually quite cute. Yeah, the history of it is cute. And it is not a BFT system, Byzantine fault-tolerant system. So people that do distributed systems engineering might know the property of Byzantine fault. Yes, for distributed systems, they can be Byzantine fault resistant is a class of, as an error class or also an attack class. And it means that certain components in the system can give wrong answers and still the system as a whole will reach the right answer. Yeah. But Bitcoin is not Byzantine fault tolerant. It doesn't use a Byzantine fault tolerant consensus algorithm. This is something many people get wrong. So if you will read blog posts, you will always read about the Byzantine generals problem and that Bitcoin solves it. But it does not do with a Byzantine fault tolerant algorithm. It just uses a clever way with this proof of work algorithm and these statistic properties I mentioned earlier to be statistically resistant to double spending attacks unless you control more than 50% of the so-called hash power of the whole blockchain network, which also but happened in the past. So there have been attacks on the Bitcoin blockchain in the past. And then the interesting thing is it is incentivized. So participation as a node is incentivized by transaction fees that then the miners get. Yeah, and this is actually also a clever idea, but it blew out of proportion because of the nowadays speculative nature of Bitcoin. Just for completeness sake, a bit of the name history of blockchain. As far as my research goes, the first mentions of blockchain as a concept and as a data structure are in the PhD thesis by David Shaw from the 80s. So it's actually a bit older. And interestingly, he there cites another paper from a German mathematician and cryptographer from the 70s, where he also talks about chaining blocks, yeah, but it's in a little bit different context. In this context, it's more about encryption. Yeah, still, I find it interesting that the history is much older. And David Shaw, if you look into him, interesting guy in the 80s, in the 90s, he was doing a lot of digital cash stuff. He also had companies, but it did not really work. He was using different concepts, a lot of cryptographic mechanisms, and maybe they were even safer and more scalable as blockchain is in some ways, but they were also more centralized. Yeah, but ultimately his stuff did not succeed, but he's still a very important person in the historic context of this whole blockchain topic, in my opinion. So yeah, let's have a quick look at how the blockchain data structure looks in this case, in the case of Bitcoin, but most blockchain data structures look something like this. And this is where also the name comes from, those blocks chaining together. And you chain them together by means of hashing them. And the hash of the previous block is the input into the hash of the next block. Now, that's how it works. And this is how it works concretely at the bottom here, how it works concretely for Bitcoin. So you have a couple of things in the header of your block. Yeah? This is the hash of the previous block. It's some transaction metadata, more or less. Yes, this has a Merkle trees, but we don't go into the detail of this. And then a free field nonce. We will talk about this in a bit. Yeah. Then you hash this together. This then becomes the input of the next block again. And now the secure thing is if you manipulate a block somewhere at the back, you would need to rehash everything. And this is a security so that you can't manipulate historic entries in the ledger. That's the idea of the blockchain. And like the previous blocks kind of get sealed by each additional block coming afterwards. Now, the proof of work has also a really cool history. So it has been, to my knowledge, first mentioned in a paper from '92 by Dwork and Nauer. And that was called Pricing via Processing on Combating Junk Mail. And it was the idea to use it as a way to combat junk mail, that basically you have to invest a little bit of computing resources to be allowed to send an email to someone. And then if you use email in a normal way, it's still cheap as always. But if you just send thousands, millions of spam mails, you have a lot of computing cost. Then in '99, I'm not even sure if they knew about the other paper or mentioned it, but there was another paper that then mentioned the name the first time, Proofs of Work and Bread Pudding Protocols from Jacobson and Jules. And they're the same idea, more or less, but the idea is to use the outcome of this computation for something useful. And in this case, they were thinking of calculating hash collisions, and these hash collisions then become some kind of coins already back then. It's called micromint. There's a concept from Rivers and Shamir, also famous cryptographers, but I never looked into this actually, what is micromint. Yep, but so in which times these were? These were '92 and '99, yeah, okay. But then '97, Adam Back invented a proof of work algorithm called Hashcash. And this is the one used also in Bitcoin. Now, this is exactly the same concept, yes, for limiting the abuse of unmetered internet resources in this way, like also same, sending spam mail, so against junk mail in this case. And how do you solve this proof of work? You find a hash collision. So you get a header from your email basically, and then you have to increment a counter value until you find a hash with, for example, in this case, 5 leading zeros. Yeah. So this is the input, and at the bottom here is the counter. And this is a solution for this. They always call it a cryptographic puzzle, yeah, for this proof of work. Yeah, and this is exactly what Bitcoin uses. Exactly. So we can check this out in Java, but maybe only if we have some time left in the end, because it's so simple, it's also not so interesting, I think. Yeah, but maybe if we have some more time, we will look into this. I want to go a bit further to reach the Ethereum topics. But that's what the mining does in Bitcoin, yeah? So it increments a counter by 1 until it finds a partial hash collision. So a hash starting with n zeros. That's all. That's how the energy gets used in the proof of work in Bitcoin. Okay, another important property, there are different concepts of blockchains nowadays, consortial, public, private, etc., etc. But in general, the community says for something to be a real blockchain, it has to be an open blockchain, and for this it has to follow these 5 pillars: being open, borderless, neutral, censorship resistant, public. In a way, it means everyone can participate, everyone can run nodes, everyone can verify the correctness of the transaction, etc., etc. But in practice, there are many different classes of blockchains we see out in the wild, and a lot of projects use blockchains in a way where you would not say this is not a blockchain anymore. Yeah? But we have the one extreme at the top right quadrant here are the public open blockchains, something like Ethereum and Bitcoin, and those mostly work with those proof of work based consensus mechanism. Proof of stake would be a different one. And then in theory, you have a completely different class, private closed or private permission, they are sometimes called, where people not even can look into them. They are just then used, for example, by a group of companies when they operate a blockchain network together. A lot of the more, I don't know, industry-focused blockchain technologies you can find are in some of those, like private closed or private open. And the usefulness of those is also questionable, as opposed to maybe just using other classic system architectures, other databases, whatever. So the Hyperledger project, if you ever heard about the Hyperledger, there are many different blockchain technologies in the Hyperledger umbrella project from the Linux Foundation. They mostly are in those below quadrants here. Okay, but now let's go to the exciting stuff, to smart contracts and Ethereum. But I again want to start with a small history nugget, and that is about the sentence, code is law. So there is always the notion by the cryptocurrency community and the blockchain community that Lawrence Lessig used to say, code is law, yes, and that therefore what we encode in the smart contracts can be law, and we can encode our laws using smart contracts, and what they execute, that has to happen, kind of, yeah, that will be the law. But I just want to say that's never what Lawrence Lessig said. So if you read this kind of thing, that's just not true. What he said in his essay, Code is Law, he warned for the dangers when the technology companies and technology will start through their innovation to force laws onto society. And society and lawmakers are not fast enough to adapt their laws to the developments of technology and cyberspace. So it's a completely different what he said. And what he said is very important. We should think about this in terms of GDPR, etc. In the European Union, we have a lot of these kind of laws running behind the technology makers. Yeah, but this is just, I like to clarify this every time I talk about this topic. Oops, yes, this is the man. Okay. But smart contract as a concept, where does this come from? Again, older paper from this 90s, 97, from Nick Szabo. And he had an article derived from this paper, and this was called The Idea of Smart Contracts. And he gives an example for a very simple smart contract. This is a vending machine, yeah, and it is so the vending machine. Also nowadays they operate with some code and they do automated business transactions from whatever logic. And most importantly, the vending machines, like if you get I don't know, like a Coca-Cola or so, they also trigger some side effects in the real world. That was kind of the exciting thing for him. So in this case, like the motor will is kind of a robot, yeah, a vending machine, or like it will physically give you access to the drink. So that's kind of cool. And he was thinking something similar, for example, for cars. So if you would have a leasing car and you're accessing the car using some kind of cryptographic key mechanism, which we probably do in modern cars in those wireless keys, but I'm not sure. But you would use like your private key. The same private key you would also use for sending transactions in whatever, money somewhere. And then the car would look, okay, was the leasing rate paid? Kind of associating it based on the cryptographic identity. And if the leasing rate was paid, then it would only turn on. So adding kind of smart business logic and computing into business transactions and the side effects of the business transaction, encoding it, everything together. That's the idea of it. That's the idea of it, but that's not necessarily what the smart contracts in Ethereum are. So what is Ethereum? Yes, one might say it's the second largest cryptocurrency platform next to Bitcoin. 2013 from Vitalik Buterin, described in a white paper. And then 2014 developed and implemented by Gavin Wood, and in a yellow paper, and he wrote something called the Ethereum Virtual Machine, EVM, very similar concept to Java Virtual Machine, maybe. And this is a quasi-Turing complete machine, this EVM. And yes, it is also running in a distributed network. And it has something called rich statefulness, which is cool. So it's a little bit similar to object orientation. So objects, they have a state. Objects in Ethereum, the smart contracts are nothing but objects, by the way. They have a rich state, meaning they always have a historic or the record of all its historic states. and the events that changed its states. That is rich statefulness in this context. And Ethereum supports a new class of applications. They are called Dapps, decentralized applications. And these are applications, for example, web applications that have part of their logics in smart contracts that run then on Ethereum. And there are different Ethereum networks based on the Ethereum technology. So if you think Ethereum, yes, there is the Ethereum network, but there are different Ethereum networks, and they also use Ethereum. So it's a little bit confusing, yes? And then there is a cryptocurrency. This is called Ether. The famous big Ethereum network is the Ethereum mainnet. And then we also have something called Ethereum Classic, which is a previous fork, a historic fork, not so important. But we have also other kinds of networks. Bloxburg network is quite cool, and I used to be involved with it. This is a scientific network run by universities. Okay, and now we see some smart contract, finally. Yeah, so that's how a smart contract looks. And we will actually check this out in code. Yeah, so yes, let's check this out in code. It's more fun. So yeah, I'm having the same here. This is my smart contract. It is written in a language called Solidity. You can also write smart contracts in other languages, but Solidity is the most widespread one. It looks a little bit like JavaScript in a way. And this now needs to be compiled into Ethereum bytecode. And this Ethereum bytecode can then run on the Ethereum virtual machine. Now, what does this mean in practice? As a Java developer, there are a couple of cool libraries we can use. And maybe for this, I go quickly back onto this slide. And the most convenient library is called Web3j, open source library. And the idea is, on the right side, you see the Ethereum network. So you have all those different Ethereum nodes that are talking with each other. Some are miners, some are just validators, and they will execute transactions and so on. And those nodes are also called clients. Yeah? So that is important to know. The nodes, the Ethereum servers, so to say, are in Ethereum lingo clients, Ethereum clients. And you can connect to them using an API or a web port, and then you can speak with them, call their functions, send transactions using JSON RPC. And this is what Web3j does. So it gives us a Java API to interact with just any Ethereum client somewhere using JSON RPC. And your Ethereum client, this client, for example, could be on my local machine, and that is even how I will show how it works. And then it connected via peer-to-peer with a network. Okay, so I'm having the Web3j library, and then there is a cool Maven plugin, Web3j Maven plugin. And this Maven plugin allows me to, one second, Maven gives me this Web3 generate sources target. And when I run this, which I run before already, so nothing new will really happen. But what it does, it takes this smart contract code, does some stuff, okay, and it generates a Java class, this class here, storage. So 1 second, maybe again, so this contract is called storage, and it's actually just the same as a Java class. So smart contracts, think about them as Java classes. And deploying a smart contract onto the network is basically the same as instantiating an object based on a class. So that's how you should think about it. It's really object-oriented programming in a distributed system. And that makes a lot of things more logical, in my opinion. And we have a super simple class here, smart contract, yeah, not class, smart contract, and it can do nothing but store a value, in this case, a number. So it has a number as a field, and it has two functions, a getter and a setter, so to say. The store function takes a number and it stores it, and then a retrieve function that just returns the currently stored number. That's all. Okay, now how to interact with it. I'm using now Docker to, I wanted to, no. Close pane. I don't want it to open it here in the side. It makes more and more. Someone knows how I can close in the presentation mode those views. If yes, split, unsplit all maybe. Cool. Yeah, I just learned. So if you press Alt and clicks, then it splits automatically. I didn't know before. So I have this Docker Compose file, and in this I use something called Ganache. Ganache is just a tool to run a local Ethereum single node cluster, so to say, a single node network for development purposes. Yeah, and it works quite nicely. And I have it already running. So I have a Ganache, so a local Ethereum node running. It's not connected to the public Ethereum network. Yes, I'm running in a test network. So I have this running here. And now what I need to do when I want to interact with this Ethereum, this Ethereum node, this Ethereum client from Web3j. I construct a Web3j client, and you can use different mechanisms to connect with it. Now I'm using the HTTP service here. It can be a Web3j service. 1 second, let's check. So a Web3j service, and Web3j services can be a HTTP service, but also IPC service, Unix IPC service, WebSocket service, and so on. So you can, for example, connect to it using Unix socket. That would also have been possible. I could have mounted a Unix socket into the containers, and it would be a faster connection. But web is okay, and it also kind of demonstrates how you would connect to a node on the network, for example. Okay, we connect to it using HTTP. Then we now establish our identity by specifying a private key here now. This is now a dummy key. Each time you start this development node, it creates a new dummy key, and I just hardcoded it here now for more. But you can also like create. There were some other mechanisms to load them from files and so on. I'm not sure yet at the moment, but yeah, you would normally load this from somewhere, from your wallet file or whatever. This is your private key. And now we deploy the contract. And how do I do this? I do this using this storage class. And this storage class has been generated by this Maven goal. This Maven generate sources. And this is a Java proxy. It's a Java proxy that provides me like the constructors and all the functions that the smart contracts defined, but interacting with it is actually like something like RMI, yes, like a remote interface to this distributed object. Still quite convenient in general. And here we see this is the Ethereum bytecode, so this is the compiled smart contract. And now we deploy it into our network. Deploying is like instantiating an object. Now we have to use something called a gas provider. I didn't talk about this in detail, but basically every transaction in Ethereum costs gas. This is the utility token of the network by which the computation is paid. Yeah, and different operations in a smart contract cost different amount of gas. And then the miners that execute those smart contracts, they get the gas fee for executing them for you. Yeah, and here we specify for which price and until what limit we are ready to pay gas for deploying our contract. And how much we have to pay for a contract depends on how big the contract is, for example. So I deploy it, and afterwards I can interact with it nearly like with a local object. So I call here, for example, the retrieve function, and now the retrieve function is, if we look, let's look at the type of it. It is a remote function call. And now we can decide to interact with it using different mechanisms like synchronous or send async. And there are also some reactive mechanisms which are flowable. Yeah, okay. But for simplicity, we just do a synchronous call now. Yep. So we check what is the initial value. the initial value should be 0 probably, unless I also already ran it before. Maybe I ran it before. So we show the initial value, and then we can set values and retrieve again. And yeah, not a lot of magic happening here actually. Okay, so yes, the initial value was 0. Then we set 4711, then we set 42. And if I now run again, since the node is still running in the background, we should start with 42. No, we don't start with 42. Why do we not start with 42? Because we deploy a new smart contract here. This is also a transaction. This smart contract has its own state, just like an object would have its own state. It had its own address, just like an object has a memory address. And we can look at its address. It's interesting. I hope it will be easily visible with a breakpoint here. So I made a breakpoint here. And if we look into this storage smart contract, we see here, this is the address. Yeah? The address of the smart contract in the network, just like we would have a memory address of a Java object in the JVM. All right, okay. So yeah, as you can see, interacting with smart contracts from within Java is like interacting with remote objects in a way, and it is like this because they are nothing different than remote objects. And because of this, they are so generic, you can, and they are Turing complete, you can do everything with them. And the name smart contract, in my opinion, is not good because they are just distributed objects. They are not necessarily smart contracts. You can use those Ethereum smart contracts to implement semantical smart contract, but you can also use them to implement game of life or do whatever you want. Okay, there's also a cool project from the Web3j folks, Web3j unit that uses test containers underneath, and you can kind of integration test your smart contracts, your Solidity smart contracts directly. It's quite cool. It spins up the Ethereum node then directly using Docker. Yeah, that's how it looks. You annotate the class. And yeah, this is kind of funny. So of course, there are completely different classes of blockchains. If we look at Oracle Cloud, for example, they had the Oracle blockchain platform. This was all this Hyperledger stuff, yeah, where I said, okay, if you're going in this Hyperledger direction, you really have to ask yourself, do you even need a blockchain or are other technologies better? Especially considering that many of the Hyperledger projects are not always super actively maintained and so on. So just be careful if you are touching those Hyperledger projects, make sure they are still lively. And there's a funny feature in Oracle when you see the Oracle database, blockchain tables, where they become append-only tables and they chain each other with a hash field in their database table. And for many use cases where people need blockchain, that's probably all they need, yeah, such a hashed append-only table in a relational database. I would strongly consider this unless you really have use cases that require those special distributed trust and censorship resistant world computer, which many people don't have. Cool. Yes, I wanted to actually finish 4 minutes ago to have some more time for questions, but I finished now. So we have 6 minutes left for questions. If you have any questions, do so please in the chat. And actually, I'm not sure what happened now. Some breakout room thingy popped up. But yeah, if someone has any questions, ask me, please. I'd be happy to answer them. Could be all kind of questions. Okay, have I looked into IOTA and the smart contract protocol? What's your opinion about? So I haven't really, I had no hands-on experience with IOTA. This thing with IOTA that always rubbed me the wrong way is that it is very, very centrally controlled. Yes, so in this way, it was never a real blockchain technology in the sense of those open blockchain pillars. And you saw this in the past because the operators of IOTAs were able to stop the stop the network when some catastrophic bugs appeared, or I think also like roll back some things. And this is of course good in a lot of system design, but blockchains generally don't allow this. So if you see this happening, that already means, okay, this is not a real decentralized system in the blockchain sense. You still have some central entities controlling it. And then why have a blockchain in the first place when you still have a small group of centralized entities? But I can't tell anything more about the technical capabilities of their smart contracts. Sorry there. Atomic Jar is zero active in the blockchain landscape. And so far we have zero plans for the future to change this. So I'm just personally still a bit more active until my PhD is done. Then Erwenig is asking, is it possible to import a contract into another contract? If yes, does the Maven plugin support this when generating sources? Indirectly, this is possible, yes. So you can call other contracts from one contract. So this always changes. Yes, there is a lot of change in the syntax and the features of Solidity. But back then, when I was using it, you could not do it. Oh, there are two ways to do it, yes. So you can do something like import, like a Java import or like a JavaScript import. And then what would happen that you get one big smart contract as a single compile instance, as a single deployment unit. Then you deploy all those smart contracts together. They are a single unit. This is possible. Another thing that is possible is that you call other smart contracts that are deployed somewhere else in the network, also in other points in time. And that is generally the elegant way to do it, I would say. And then you can kind of instantiate another smart contract from within your smart contract code. Just say, okay, I want to call a smart contract at this address, and then you call its function. This is all part of the same transactions then. And then the important thing is to have a composable, updatable smart contract is to inject the address of the other smart contract you want to interact with somehow, like through something like setter injection or whatever, that you can then update your smart contract to point at a new other collaborating smart contract. Yes, so that's some about this. How and when would Ethereum hit this limitation in terms of resources? Could you elaborate on some use cases for on-chain, off-chain operations? Yeah, so I still plan actually to do a game of life in Ethereum, also as part of my PhD, to just basically showcase how incredibly slow it is. So you can do something like Game of Life, but it's super slow and super, super expensive, especially if you would do it in a public network. And yeah, like, I don't know, you can't nearly do anything except some simple arithmetics, I would say. Like, that's the only things you can do. And then everything else you should calculate off-chain and then just save hashes on-chain. Yeah? So you also can't save big amounts of data on the chain because it becomes just so incredibly expensive. So that's why everyone is just saving hashes or saving pointers to the data. Yeah. So the static gas provider, someone asked how it works. It just uses for every transaction the gas price of what is this, 100,000 and gas limit of 100,000. It just works because my test node will work with those values. If you're interacting with the real Ethereum, you have to always look at the contention of the network, because high contention will bring the gas price up. Gas limits is the number of gas units you are maximum willing to pay as part of your execution. This is for protecting you against infinity loops in the smart contracts, because the smart contracts will terminate when it runs out of gas, and it will maximum take from you this amount of gas units. Then the price you have to actually pay is the amount of used gas by the contract times the gas price in Gwei. In Gwei or in Wei? Sorry, I'm not sure. Gwei is gigawei. Wei is a sub-unit of Ether. Yeah? So ultimately, this comes down to a subunit of Ether. Yeah. So if in this case we use 10 gas units, it will be more expensive, but just assuming it was 10, then it would be 10 times 100,000 Wei. Yeah, that would be the cost. But there are other gas providers. So, for example, Dynamic. There should be one. Let's check here. No, actually not. Yeah. So the alternative, by the way, is that you implement your own. Obviously, like before there was a different way. You could just specify limit and gas price for the transaction, but they deprecate this. Now you should use this gas provider, contract gas provider. Yeah, then the default one just uses defaults. Yeah, okay, so you have to maybe use your own then if you have more complex mechanisms. Cool. Okay, so someone else also asked, could David, if I understand correct, a smart contract's purpose is to decide on reaching consensus about transaction. Can blockchain also be used just for the sake of context? In other words, agreeing with multiple nodes on a certain contract and use the blockchain to check if their agreement still applies and which expires at some moment in the future. So the smart contract's purpose in the context of Ethereum is really just having an object, and what you encode there, you can do whatever you want. Now the state of the smart contract will be synchronized over the whole network, and the state of the smart contract can only be changed by means of events going in. Those events going in can only be calls to the functions from the smart contract. So you always have to give a stimulus from the outside into the function, into the smart contract via the means of a transaction. Yeah, so the smart contract does not reach the consensus over the transaction. This is what the Ethereum blockchain itself does. So the transactions that go in trigger execution of methods in the smart contract. And what this then, and then the state will be synchronized via the consensus mechanism of the underlying blockchain. What you encode in this on the business level, that's up to you. Can anyone call these functions? Yes, anyone can call these functions. You need to have an identity in the Ethereum network, but everyone has already identities. So the moment you are generating your private key pair, public-private key pair, this is your identity. Yes, anyone can just call it. So everything is public for everyone. And Richard is just telling me I have to wrap it up. So I do it now. Thank you very much. I hope you learned a little bit more about Ethereum, and maybe you understand it better. You like it more, you like it less. I don't care. But thank you. And yeah, if you have any questions, follow me on Twitter, etc. pp. See you in the test containers world as well. Have fun. Bye-bye.